Good morning, children. Welcome to today's maths class. Now, the fifth problem from the exercise 1.1. Use Euclid's divisional lemma to show that the cube of any positive integer is of the form 9m, 9m plus 1 or 9m plus 8. Okay? Let us go with the answer. Now, let us take for any positive integer a and b is equal to 3. By Euclid's divisional lemma, we can write it as a is equal to 3q plus r. Why? Because here the divisor b is 3. As per the Euclid's divisional lemma, we can say that a is equal to bq plus r. Where b is 3, we can take a is equal to 3q plus r. Here q is quotient and r is remainder. Such that 0 less than or equal to r less than 3. Why? Because the remainder is always less than the divisor and it must be either 0 or more than 0. Therefore, the remainder lies in between 0 and 3. Okay, and also 0. Now, if r is equal to 0, then we can write a is equal to 3q plus 0. That is a is equal to 3q. If r is equal to 1, then we can write a is equal to 3q plus 1. If you take r value 2, you'll get a is equal to 3q plus 2. Okay, let us check these three cases. For a is equal to 3q, by cubing on both sides, we get a cube is equal to 3q whole cube. That is equal to 27q cube. We can write it as 9 into 3 cube. 3q cube. So this is 9 into something. Let us take this 3q cube as m. Since q is an integer, 3 into q cube is also an integer. So m is an integer, 9 into m. Okay. Now a cube is equal to 9m. This is the first part. Now let us go with a is equal to 3q plus 1 and cubing on both sides. We get a cube is equal to 3q plus 1 whole cube. By applying this algebraic formula, a plus b whole cube. What is a plus b whole cube? A cube plus 3a square b plus 3ab square plus b cube. So by using this formula, we can write a cube is equal to 3q plus 1 whole cube. That is equal to 3q whole cube plus 3 into 3q square into 1 plus 3 into 3q into 1 square plus b cube is 1 cube. If you simplify, you will get like this. And you can take 9 common from the first 3 terms. We get 9 into 3q cube plus 3q square plus q plus 1. So let us take this part as m. Okay. So this is also an integer. M is equal to 3q cube plus 3q square plus q. Then this can be written as in the form of 9m plus 1. So this is the second part. Now let us go with a is equal to 3q plus 2. a is equal to 3q plus 2. And let us cube on both sides. Then we get a cube is equal to 3q plus 2 whole cube. Now by applying the same formula, a plus b whole cube, we get a cube, 3q cube plus 3a square b. Here a is 3q and b is 2. And 3ab square. A is 3q and b is 2. And b cube is 2 cube. If you simplify, you'll get this. And you can take 9 common from the first 3 terms. We get 9 into 3q cube plus 6q square plus 4q plus 8. So this can be written as 9 into something plus 8. This something 3q cube plus 6q square plus 4q, take it as m. So this can be written as 9m plus 8. Now look at these all 3 cases. Here we get a cube is equal to 9m. Here a cube is equal to 9m plus 1. And here in the third case, a cube is equal to 9m plus 8. So from 1, 2 and 3, we have a cube is 9m, 9m plus 1 and 9m plus 8. Okay, therefore, the cube of any positive integer can be in the form 9m or 9m plus 1 or 9m plus 8. Okay? Now look at the exercise 1.2. The first Roman. Express each number as a product of its prime factors. Okay, now look at the first one, 140. Here 140 can be written as 2 into 2 into 5 into 7. We can write the prime factors in this way. In the division method, we get 2 into 2, 2 square into 5 into 7. In the same way, we can do the other problems. 156 can be written as 2 into 2 into 3 into 13. Okay? So like this we can do these all problems on yourself. So in this way we need to find the prime factorization of the given composite number. Okay? Now look at the second Roman of the exercise 1.2. Find the LCM and HCF of the following pairs of integers and verify that LCM into HCF is equal to product of two numbers. Okay, now already in the exercise 1.1 we have learned how to find the HCF of two numbers by using Euclid's division lemma. Okay, here we are going to learn how to find the HCF and LCM of any two given numbers by using prime factorization method. Okay, here in the first problem he has given that 26 and 91. So 26 can be written as 2 into 13, 91 can be written as 7 into 13. Here we have done the prime factorization in the rough work. Okay, now here you have to learn these 2 points. These are very important. We need to follow these 2 points to find HCF and LCM of any two numbers by using the prime factorization method. Okay, these are very important points. First point, HCF is the product of the smallest power of each common prime factor in the numbers. Now look at the prime factorization of the given two numbers. 26 is equal to 2 into 13 and 91 is equal to 7 into 13. What is the common factor among these two? Actually, the smallest power of the common factors we need to check. There are no powers, so we can take the common factor directly. The common factor among these two is 13. Therefore, the HCF is 13. In this way, we have to learn this point to find the LCM of any two given numbers. That is, LCM is the product of the greatest power of each prime factor involved in the numbers. Now, let us take each factor of these numbers. So, among these factors, 2, 7, 13 are the factors. Okay, we need to take the greatest power actually. As there are no powers, we can take all the numbers. Okay, 2, 7, 13. Among 13, the greatest power, there is no power, so we can take 13 only. So the LCM is 2 into 7 into 13. That is 182. Let us verify. What is the verification? LCM into HCF, otherwise HCF into LCM is 13 into 182, we get 2366. Now let us multiply the two given numbers. What are the two given numbers? 26 and 91. If you multiply, you will get 2366. Here you observe the product of the HCF and LCM is equal to product of the numbers. In this way, we need to check whether the HCF and LCM of the given numbers are correct or not. Okay, if you multiply HCF and LCM and if you multiply the product of the numbers, we will get the same answers. So like that we can verify the HCF and LCM of the given numbers. Okay, now look at the second problem. We need to find the HCF and LCM of these two numbers 510 and 92. Okay, by using prime factorization in the rough work we have done, see, we will get 510 is equal to 2 into 3 into 5 into 17 and 92 can be written as 2 into 2 into 23. But so already we have written these 2 points. We can use these 2 points for these problems also. Okay, for this problem also. Now what is the HCF? HCF is the product of the smallest powers of the each common prime factor. What is the common prime factor? 2. So here 2 into 2 means 2 square. Here 2. What is the smallest power among the common factors? 2. Therefore HCF is 2. And what is the LCM? LCM is the product of greatest power of each prime factor. Now let us look at the each prime factor greatest power. 2, here 2 into 2 is 2 square. The highest power is 2. So we can take 2 times. Okay. Otherwise you can write 2 square here itself. We no need to write here. 2 square 3 into 5 into 17 into 23. We get this one. Okay. Now let us verify. LCM into HCF is equal to LCM into HCF. We get 46920. And what is the product of the numbers? Product of the numbers 510 into 92. We get 46920. So LCM into HCF is equal to product of the numbers. Okay. Now look at the third problem. 336 and 54. Now let us write the prime factorization of 336. That is 2 power 4 into 3 into 7. And prime factorization of 54 is 2 into 3 cube. Now HCF. So as we have learned in the previous problem, what is the HCF? The HCF is the product of the smallest power of each common prime factor in the numbers. Now let us look at the smallest power of each common prime factor. Here 2 is the common prime factor. Among these two, what is the smallest power? 2. So take 2. And the other common factor is 3. Among 3 put to the power of 1 and 3 cube, 3 power 1 is the smallest power. So we can take 3 power 1, that is 3. Now the HCF is 2 into 3, that is 6. Now LCM. Now the LCM is the product of the greatest power of each prime factor involved in the numbers. So we need to take the greatest power of each. So 2 among 2's the greatest power is 2 to the power of 4. Among 3's the greatest power is 3 cube. As there is only one number in 7's, we have to take that number as it is. So 2 to the power of 4 into 3 cube into 7. If you multiply, you will get 3024. Now let us verify. How to verify? Let us multiply the LCM and HCF. What is the product of LCM and HCF? 3024 into 6, we get 18,144. Now, let us multiply the given two numbers. Product of the given numbers is 336 into 54 is also the same product, 18,144. Now we get the same answer for these two. Therefore, we can say LCM into HCF is equal to product of the numbers. Thus, it is verified. Okay. Now, in the third Roman, so we need to find the HCF and LCM. Find the LCM and HCF of the following integers by applying the prime factorization method. In the second Roman, we find the LCM and HCF of the two given numbers. Here we need to find the LCM and HCF of three numbers. Okay. Here in the first Roman, first problem, we need to find LCM and HCF of 12, 15, 21. Okay. Let us go with that problem. Here 12, 15 and 21. If you find the prime factorization, 12 is equal to 2 into 2 into 3. That can be written as 2 square into 3. And 15 can be written as 3 into 5. 21 is 3 into 7. So these 2 points already we discussed in the previous problem. HCF is the product of the smallest power of each common prime factor in the numbers. Okay. We must learn these 2 points. These are very important points to find the HCF and LCM of any two numbers by using prime factorization method. So among these three numbers in the prime factorization, what is the common factor? 3. And the smallest power, there is, we can't check whether which one is the, so here there are no powers for 3, all are 1. So we can't check the smallest power of 3's. So we have to take the HCF as 3 only directly. And LCM. LCM is the product of the greatest powers of each prime factor involved in numbers. So now we have to go with each and every factor in the prime factorization. In the HCF, we have taken only the common prime factors. But while we are finding the LCM, we should not go with only the common prime factors. we should go with each and every prime factor in the factorization. Now, among 2's, 2 square means 2 into 2. Among 3's, 3 is common in all. We have to, it is enough to take only once, 3 and 5 and 7. If you multiply, the LCM is 420. Okay, in the same way, we need to find the HCF and LCM of 17, 23 and 29. So once you observe, 17, 23 and 29 are prime numbers. Okay, they don't have factors more than 2. They have the factors only 1 and itself. So they can be written as 17 can be written as only 1 into 17, 23 can be written as 1 into 23, 29 can be written as 1 into 29. Okay, they don't have any other factors. So we can write like that only. Now, what is the HCF? So this is the common rule. The HCF of any two or more than two, any coprimes is 1, as there are no common factors. Therefore, the HCF of these three numbers 17, 23 and 29 is 1. And one more point. Okay, the LCM of any coprimes is the product of the numbers. Okay, so the LCM of 17, 23, 29 is equal to 17 into 23 into 29, that is 11,339. Okay, whenever you have the prime numbers, we can take the HCF as 1 and we can get the LCM by multiplying the given numbers directly. Okay, now in the exercise 1.2, as of now we have learned how to find the LCM and HCF of the given two numbers, and also we have learned how to check whether they are correct or not by using the formula LCM into HCF is equal to product of the numbers. And also we learned how to find the LCM and HCF of the three given numbers. Okay, in this process we have learned the points. HCF is the product of the smallest power of each common prime factor in the numbers, and LCM is the product of the greatest power of each prime factor involved in the numbers. So by learning these two, you can find the LCM and HCF of any two given number, any two or more than two given numbers. Okay, so we'll continue the exercise in the tomorrow's class. Thank you. Have a nice day.